honored to be here to talk about my work on advancing human-machine synergy for this future of surgery. And so throughout the duration of my talk, I will be talking about how this perspective shapes my current and my future work. So in the past decades, we have been observing a digital transformation in surgery. And looking forward, current advancements in robotics, AI, and surgical navigation is showing like a future with much increased autonomy and precision. However, there's a parallel imperative to increasing the capabilities of these systems. We also need to make sure that it is safe and that we can actually assure the safety of these systems. And so we need to know like whether the system is doing the right thing at the right time. And so my research focuses on how we can actually assure this type of safety. So to address this challenge, I have three focuses. The first one, can we actually enable human operators to verify these autonomous system of outputs? The second is, can we design machines that audit the system and verify the results? The third is, can we foster human-machine partnerships to actually share this type of oversight of the system planning and execution? Much of my work so far has been focused on image-guided surgery for orthopedics. So as of now, we see that a lot of the robotics and the navigation are showing a lot of promise in this image-guided orthopedic surgery. And one of the key enabling factors for this image-guided orthopedic surgery is to know the relative poses of the anatomy, the tool, and also the imaging system. And one autonomous algorithm that I have been exploring in my work so far is 2D 3D registration. And for those who are not familiar with 2D 3D registration, I will briefly go over what that is. So the goal of the algorithm is to find the object that you're interested in with respect to the projective imaging geometry. And so intraoperatively during the surgery, you would have a 2D X-ray that you can take at any time. And preoperatively, you will have a 3D CT volume. And with that, the algorithm starts with an initial pose of that 3D volume and creates a digitally reconstructed radiograph with that initial pose of that 3D volume. And the algorithm reiteratively goes through different poses, each time generating a different DRR and comparing it with the intraoperative X-ray. And once it finds the DRR that most closely matches with the intraoperative X-ray, we are able to estimate the pose of the intraoperative object that we want to find a pose of. There are many benefits to this image-based 2D 3D registration, including that you can estimate the anatomical pose without the use of external trackers. It leverages the standard imaging systems like X-ray and CT, and it's also cost-effective, and the workflow is not disrupted because we're already using the images that we need to be using during surgery. However, there are some challenges to this algorithm, one of it being that it can sometimes output inaccurate results that are well over the clinically acceptable margin of 2 millimeters of mean target registration error. And the problem is during surgery, system errors cannot be detected automatically. And thus, there is a critical need for the safety assurance of this registration algorithm. To start, we started to look into the question of, can we involve human operators to verify the results of 2D 3D registration? And in order to do that, we first asked, what is the kind of information that we can give to the humans to actually do this task? So in current practice, in a lot of the 2D 3D registration literature, what people have been doing was you take the final DRR from the registration results, you compute the edge map, and then you overlay that information onto the 2D X-ray. And so we call this the neutral existing paradigm. But then we also question the efficacy of the neutral paradigm to allow the human operators to verify the 2D 3D registration results. And thus, we created two novel paradigms, the first one being attention guiding, where we give cues of misalignment to ask the operator to take a second look in these areas of mismatch. The second visualization paradigm that we created was called correspondence suggesting, where we actually provide arrows of the correspondences that are suggested by the algorithm. And then we performed a user study with these 3 visualization paradigms to see how the human operators perform on the quality assurance task. And as you can see, the users were able to differentiate between 4 different types of error groups on average. So we also observed that there is a strong accept or strong reject in all 4 of the error groups. And so we believe that more investigation was needed for this human-based assessment of 2D3D registration quality. And so we also asked, like, do the visualization paradigms affect the assessment performance as well? And we found that the novel paradigms that we developed outperformed the neutral method. And we also saw that all 3 visualization paradigms perform better than random guessing. However, we did see that the overall accuracy is still low, and so we wanted to do a more deeper investigation. And to do that, we actually wanted to use gaze to see if we can understand the judgments that the humans are making. And so we observed qualitatively that the gaze patterns that you see as heat maps here differed depending on the cases that they saw and also the different visualization paradigms. And so we tried to quantify these gaze patterns as gaze metrics, and we saw that the user's assessment error is inversely correlated with the fixation count and the fixation duration, which are some of the gaze metrics that we computed. And so we found out that some gaze metrics can actually predict the human-based assessment performance. And as for the visualization paradigms as well, we saw that there were significant differences in terms of which visualization paradigm that they looked at and the gaze metrics that were computed. And so we found out that it's not only what information is given to the humans that matter, but also how the information is given. To move on, we also were curious about whether we can design the machines to audit the system. And so first, for a non-learning based method, we quantified uncertainty using a probabilistic method, and we wanted to investigate the relationship between uncertainty and the registration accuracy. We found out that the registration accuracy and uncertainty metrics have a non-linear relationship. And we also saw that the relationship actually varies across the errors. And so we are able to predict the error when you're able to use the uncertainty metrics when the errors are lower in a more accurate way than when the errors are actually higher. For a learning-based method, we also made the first attempt to train an AI specifically for doing the quality audit of 2D3D registration results. We took the input of the X-rays and the DRRs in a concatenated way, and then we used a CNN with cross-attention and outputted a binary whether it should be rejected or accepted. And we found out that the model achieved about 0.76 accuracy. And we found out that the AI model is indeed capable of distinguishing between the correct and the incorrect registration results. However, there is definitely room for improvement for this performance. And so finally, moving on to the human-machine partnerships and whether we can foster that to enable this type of oversight. We did a comparison between the AI only, human plus AI, and the human plus explainable AI. And so for the explainability features, we use GradCam to show visually where the model's attention goes. And we also use conformal prediction to show the model's confidence. And so in the case of the human XAI condition, the user interface looks something like this, where you would see the AI's assessment, and you would also see the certainty and the probability of accept versus reject, and also the visual heat map of the GradCam. What we did find was that the human AI conditions result in higher accuracy than the human only. However, we did also see that the AI only results in highest accuracy. And so in future directions, we aim to improve the model performance for registration quality assessment and also try to balance the visual load that the user is given, because there's a lot of information that's given, but we believe there could be a way to trade off the visual load with the interpretability of the information that we give. Second, the information that was given was mostly static, so we want to develop more interactive forms of explainable AI. And third, we want to try to incorporate the gaze of the human operators for real-time interaction and adaptation. And another aspect that we observed while we are running these types of user studies is that these types of user studies, not just ours, but many human-machine interaction studies, are conducted in a very standard office-like environment. And so this made us question, will this actually be able to capture the human behavior when the stakes are real, like in actual surgery? And so we created a contextually realistic environment in the mock OR that we have in our institute. And we had a phantom covered with drapes and also an active robot that moved accordingly to the decisions that the human made. And so comparing this in a between subject study, in the mock OR environment, as you can see in this video, when the user accepted the registration result, the robot actually moved and made an insertion into the phantom. And so the user was able to feel that whatever decision that they make is actually going to matter. So that was the study that we ran. And we found out that with the same task and the same machine outputs, the human response changed. We found that the engagement and the interaction increased significantly when the users were in the contextually realistic environment. And also they perceived a much higher stakes in terms of how careful they were and also the impact that they felt that their choices would have. And finally, they also perceived a higher mental load despite the task being exactly the same in the two conditions. And so for future directions, we want to investigate how to design more ecologically valid human machine evaluations, meaning try to design studies where its findings can actually apply in the real world settings and not just stay in the lab. Also, we also want to explore how to model the human state using gaze and also other physiological signals like electrodermal activity. So finally, I want to recap that my work looked into understanding of like the human, the machine, and also how to design and evaluate these human-machine partnerships. And the ultimate goal is to improve the safety assurance of these evolving surgical technologies. And so far, I have only focused on 2D 3D registration, but I strongly believe that this can be applied into many of the other autonomous technologies that we're developing. So thank you. And my email and my personal website are here, and I would love to connect and collaborate and learn more. So thank you very much.
I saw the picture where you had the kind of pelvic X-ray and they had it misaligned.
Mhm.
There was the AI determined that it was misaligned and asking the user, is it aligned or not? Are you able to like how much sort of intentional bias can be produced by getting the data from what AI determination was to the clinician provider and seeing how those two things independently interact with each other to their decision making?
Yes, so in the study, we actually wanted to use the AI as a second opinion rather than it giving its output first. So the user would give their own output and then see the user's, the AI's output and determine their final decision.
The opposite where they